Hello everyone. In this lecture, we are dealing with vibrational spectra of polyatomic molecules. In the last lecture, we start lecturing about the vibrations of polyatomic molecules. We discussed the normal modes of vibrations of water and carbon dioxide. We have found an equation for finding the normal modes of vibrations of molecules. That is, for n number of atoms in a molecule, if the molecule is linear, there will be 3n minus 5 vibrational degrees of freedom or normal modes of vibrations for the molecule, and for a non-linear molecule there will be 3n minus 6 normal modes of vibrations. Thus, if we know the geometry of a molecule, we can easily predict the number of degrees of freedom or normal modes of vibrations of any molecule. Again, when we come to the vibrational spectra of water, water has 3n minus 6 equals 3 into 3 minus 6, that is 3 vibrations, and also 3 peaks are observed in the IR spectra for symmetric and asymmetric stretching and bending. For carbon dioxide as linear, there are 3 into 3 minus 5, that is 4 vibrations. However, only 2 peaks are observed. So, in this lecture, we will discuss the selection rule for vibrational spectroscopy and how these selection rules can be determined from the symmetry of the vibrational normal modes. The selection rule remains the same as that of diatomic molecule. What is that? The dipole moment must change as the vibration passes through the equilibrium position. So, now we will discuss the symmetries of vibrational modes in order to determine the selection rules for IR spectroscopy. For that, I am taking water as an example. We will consider the vibrations of water molecule and we will determine which water vibrations are IR active. For this, we have to understand some basics of group theory and symmetry. I am not going to the details of this, but we can see readily that the water molecule contains some element of symmetry. It possesses a C2 axis of symmetry which bisects the H or H angle. Why it is referred to as C2 axis? It is because twice in every complete revolution, the molecule presents an identical aspect to an observer. In a complete revolution, 2 times molecule can present its identical aspect to an observer. Thus, hence we can say the molecule possesses a C2 axis of symmetry. This molecule has only this rotational symmetry axis, and so we refer the molecular vibrations to this axis. You know, the water molecule has 3 modes of vibrations. What are they? Symmetric stretch, asymmetric stretch, and bending. If we rotate the symmetric stretching molecule, the symmetrically stretching molecule by 180 degree, the vibrations does not be changed in character. So it is known as symmetric stretch or symmetric vibration. For this asymmetric stretching, rotation of this stretching by 180 degree produces a vibration which is in anti-phase with the original, so called anti-symmetric stretching. And bending, like symmetric stretching, also symmetric, you can easily understand from this picture also. And this angle increases or decreases simultaneously, and it is symmetric. In order to be IR active, there must be a dipole change during all vibrations. And this may take place either along the axis, symmetry axis, or parallel to the symmetry axis, or at right angles to the axis. If we take the symmetric stretch of water, it leads to the dipole moment changes that occur parallel to the C2 axis of the molecule. For a normal molecule, there is a dipole moment, and we distort the molecule through stretching or compressing. Even if symmetrically, it can change the dipole moment. You can see clearly from this picture, dipole moment value has a change in all these type of stretching. For bending also, there is a change in dipole moment compared to the normal molecule for increasing angle or decreasing angle. And the anti-symmetric structure of water, there is a component, dipole moment component, that is perpendicular to the C2 axis and also changes. And the three vibrations of water molecule involves a dipole moment change during vibration, and hence we can say that the three normal modes of water are IR active. Now let us consider the vibrations of carbon dioxide. As I said earlier, water has 4 vibrational modes, normal modes of vibrations, symmetric stretching, asymmetric stretching, and 2 degenerate bending modes. Even though it has 4, the spectrum contains only 2 bands. You can describe this by first considering the symmetric structure of carbon dioxide. You know, carbon dioxide molecule has no dipole moment. Both the CO vibrations are in phase, and as is in phase, there is no dipole moment change, that is the dipole moment remains 0 during symmetric stretching vibration. So it will not be IR active and will not appear in the IR spectra. The second one is missing as the 2 bending modes are degenerate. You know, one is in the plane and other is perpendicular to the plane, 2 vibrations. These 2 bending vibrations are related by symmetry. We can transform one mode into another by rotating about the internuclear axis. We are considering the axis through carbon. So it is called the two modes are degenerate, and so the spectral lines will lie on the top of one another. So we can see a single band rather than two. Hence, there will be two bands in the IR spectrum of carbon dioxide. The one corresponds to asymmetric stretching and the other for degenerate bending. In addition to the fundamental vibrations far discussed, other frequencies can be generated by different modulations. That we can say overtones and combination bands in polyatomic molecule. If one were able to observe the molecules of water or carbon dioxide directly, their overall vibrations would appear extremely complex, because we couldn't say that each atom would follow any one of the separate paths. Its actual motion would be essentially be a superposition of all such paths. For diatomic molecules, we have seen that when the restriction to simple harmonic motion is lifted, there comes overtones like 2 nu bar, 3 nu bar, etc. along with the fundamental vibrations. For the polyatomic molecules also, the possibility of first, second, etc. overtones occurring at frequencies near to the fundamental modes. If we are taking example of water again, water is having three fundamental vibrations. We know nu1, nu2 and nu3 for symmetric bend, asymmetric stretch and symmetric stretch. There will be having overtones in 2 nu1, 3 nu1, etc., 2 nu2, 3 nu2, 4 nu2, etc., 2 nu3, 3 nu3, etc. There is the possibility of a lot of overtones in polyatomic molecules, but their intensities fall off rapidly. In addition to overtones, the selection rule permits combination bands and difference bands in polyatomic molecules. The combination bands arises simply of two or more fundamental frequencies or overtones. That you can see here. This is if we are again taking water. If nu1 and nu2, we know the fundamental frequencies can be combined. 2 nu1 is the first overtone of the symmetric stretch. It may combine with the fundamental symmetric stretch. It may combine with the second fundamental asymmetric stretch. And the three fundamental frequencies may all be combined. Like this way, you can easily understand what are the different bands, which are nu1 minus nu2, 2 nu1 minus nu1, nu1 plus nu2 minus nu3. All these can be called difference bands. Both of these bands are allowed in spectrum, but their intensities are very small and often found in complex spectra. Thus, by this, I am concluding the details of vibrational spectra of polyatomic molecules. Thank you.